Hello and welcome to volumetric training. Today we'll be 3D scanning a 3SG cylinder head from a Toyota Altezza. I'm going to go through the process of doing a low resolution scan to establish a skeleton of our part, then follow up with a high resolution scan that we can work with. As part of the training, you can download the scan data that we've produced in this tutorial to look at and work with yourself. Let's first look at what we'll be scanning with. This is an N-Scan Pro Plus 3D scanner. It uses a process called structured light, where it projects a known image onto the surface of the object being scanned. Then using two cameras at a known distance, it can triangulate where that point is in three-dimensional space. Using this scanner, I've seen an accuracy as good as 0.025mm positional on two dowel holes 300mm apart. This information was compared to that from a CMM machine, which uses contact probing and has a calibrated positional accuracy of 0.002mm. I think that it is a pretty fantastic piece of kit for the price, considering the accuracy you can achieve for non-contact measurement. However, there are some cons to this and other scanners due to the scanning processes used. Firstly, external light sources such as the sun can cause issues with the scanning process. The scanner is trying to find positions from the images it projects. If something else is casting shadows on the part, it can cause ghosting, which you need to be very aware of. If external light source is too bright, the scanner won't even see what it is scanning as it washes out. Another issue is the surface finish. Shining metal surfaces are difficult for the scanner to see as they reflect the light projected onto it. We can get around this by coating the surface in a powder to make it matte in appearance. Scanning down inside cavities and holes can be troublesome, as the two cameras need to see the position of what it is scanning at all times. This is quite a common issue with most scanners, including some types of laser and blue light scanning. Lastly, focal range. We need to ensure that our part is positioned in a way that the two cameras can take the best image they possibly can. N-Scan software shows us that if we're too close or too far away during the scanning process. With my scanner, I've captured objects as small as a plastic hinge 20 by 10 by 5mm in size to things as big as a car. Now we know the equipment we're going to use. Let's look at what we're going to be scanning. First thing is to ensure that our part is clean of any silicon or debris. The scanner has no imagination and will capture exactly what it sees. Nothing is more frustrating than coming back to the computer, ready to start the designing process, and there is a bit of silicon in the way of the hole you want to draw. I have already lightly coated this head in a talcum powder using an aerosol can. There are brand name 3D scanning sprays available. Some of them are approved for use on plastics and materials where you want to be sure that you don't damage the part. However, CRC branded weld developer is merely talcum powder suspended in a propellant and is readily available from most tooling and industrial welding suppliers. If you're going to spray a plastic part, just check its reactivity to the propellant used. So we have our part set up on a turntable ready for scanning. First thing you'll notice is that I've covered the part in tracking dots. We need these dots to create the skeleton of our part. We're just going to go through and do a low resolution scan of our part to collect these dots and produce a P3 file that we will use for high resolution scanning. At all times the scanner needs to see 4 tracking dots. This means that you really need to have 6 to 7 dots within the scan area so that we can move along the part without losing sight of 4 of them. Another thing that you want to make sure of is that our tracking dots are randomized. If there are 2 areas where the tracking dots are identical in pattern, the software will think that our location is somewhere that it isn't. This is particularly important when doing large, slow, gradual curves in areas such as car body panels. When we set up our N-Scan project, ideally you would like to do mixed features and dots for this initial scan. This way, as we move around the part, the scanner can take position from features of the head, particularly in this initial scan process to build our frame. I like to think of 3D scanning as digital spray painting. We want to take careful, smooth movements moving backwards and forwards over the part. We need to change angles so that we can get up into hard to reach places and achieve a consistent capture all around. I have my part sitting on a turntable that I've made using a Lazy Susan from an outdoor barbecue set. Coating the turntable in black hides it from the scanner as it absorbs the light being projected. It has tracking dots on it, allowing me to quickly scan smaller parts without needing to prep. When low resolution scanning, we want to be careful not to capture any of the turntable dots. This allows us to reposition the part to get to other areas without needing to create multiple projects. If we accidentally capture any of the background, table, or generate large amounts of unwanted noise, at the end of the scanning process, hold the Shift key and draw around the area you wish to delete. Once highlighted red, simply press the delete key to remove it. We need to do this before we hit the tick and start the next scanning pass, otherwise it stores this information to file. Now we've captured our whole part with dots, we can create a STL from it for our records. We also need to save a .p3 file so that we can use the tracking positions for our high resolution 3D scan. Now it's time for our high-res 3D scan. We want to create a fixed scan project and use the .p3 file we just created as our global markers file. We now need to set up our scanner on a tripod, as the scanner will now project a series of different images on the component, improving its ability to capture the surface. We also need to set the distance from the part for the best focal range of what we are scanning. There is a target plus projected from the scanner when it is not scanning. This allows us to see the area it is planning to scan. We need the plus to be as sharp as possible. Anything it sees as blurry outside its focal range, it will disregard as noise. Now we have everything positioned, we simply press the play button and the scanner will run through its scanning process. Once complete, it will query us to see if we're happy with the results. This is where adjusting the ambient light source and the scanner's brightness is important. We want the surface it is looking at to have a slight hue of red. Too red and it will wash out the scan. Too dim and it cannot see the surface. We also need to consider shadows that the part casts on itself. As before, the scanner cannot see any area that the two cameras cannot. This is why moving around sharp right angles of a part can be difficult. We can improve our odds of capturing around corners by placing tracking dots near the edge of the part. As you can see, this process takes some time, but it gives by far the best results. Now we have captured the entire head, we can export it as an STL. We use STL meshes for our design process to reference from. Be aware that the higher the resolution of the part, the bigger the file size. Even with our modern computers, dealing with a 500 megabyte 3D mesh can be taxing on it. So depending on what your objective is for the part scanned, it may be best to reduce its resolution before exporting it to make it easier to design from. Be aware that the resolution does not decrease positional accuracy. It merely takes away points from the scan that describe the surface, reducing the detail and increasing faceting. In the next tutorial, we're going to import and orientate our mesh in CAD.